Welcome to Easy Elim Learning Simplified. My name is Ruth, and today we are going to be discussing the topic halogens, and we are also going to be looking at some of the physical properties of halogens. Previously, we had a chance to look at the introduction bit of halogens and some of the trends of the atomic sizes and the ionic sizes. So today we will basically concentrate on the physical properties and then you do a few questions to end the session. So first of all, we'll start with the laboratory preparation of chlorine gas. So chlorine gas is usually prepared by the oxidation of concentrated hydrochloric acid. This is a preparation that is going to be repeated in Form 3 as we do chlorine and its compounds, but it is important for you to see how the reaction is occurring. Chlorine is one of the elements in this group, so it is good for us to see how they usually behave. So chlorine is prepared by an oxidizing agent reacting with hydrochloric acid. So the oxidizing agent is the one that removes hydrogen from chlorine to form chlorine gas, and itself is oxidized to form water and the other products. So some of the oxidizing agents that we use for this preparation is potassium permanganate 7 and manganese 4 oxide. So when you look at the preparation of chlorine from manganese 4 oxide and hydrochloric acid, so this is a setup. You can see the dropper containing concentrated hydrochloric acid, and we have the potassium permanganate in the boiling tube. The reaction occurs and chlorine is collected in this method. So when we are reacting, it's important that we heat our reaction. So heat must be shown or must be there, and then an oxidizing agent must be there as well. In our case, we have potassium permanganate. So hydrochloric react with, in this case, it's manganese 4 oxide, not potassium permanganate. So hydrochloric will react with the manganese 4 oxide, and then manganese 4 oxide oxidizes hydrochloric acid by removing the hydrogen, resulting to formation of chlorine, and itself is reduced to water and manganese chloride. So the resultant chlorine gas is usually passed through a bottle containing water. So in our setup, we would introduce another conical flask or a conical flask containing water. The purpose for the water is to remove the hydrochloric acid fumes that would be produced, and then to remove the water or the steam in the gas, or to dry it, you'd pass it through concentrated sulfuric acid, or we would use a U-tube containing anhydrous calcium chloride, and this is to dry the gas. After the gas is dried, it is collected by downward delivery. We are going to see why it's downward delivery. So manganese 4 oxide reacts with hydrochloric acid. It oxidizes hydrochloric acid to form chlorine, and it is reduced to manganese chloride and water. So the wet chlorine is passed over sodium chloride or hot water. This is usually done, it's because it does not dissolve. If you want to collect a wet one that is not dry, you can do so by collecting it over hot water because it's not going to dissolve in water. It's less soluble in water and does not dissolve in brine. But if we want it to be dry, we have to pass it through concentrated sulfuric acid or anhydrous calcium chloride, and it is collected by downward delivery or upward displacement of air because it's heavy or it's denser than air. So then the first bottle that we talked about that contained water, we said it is done so to remove the hydrochloric fumes. So we cannot interchange those apparatus. We cannot interchange the conical flask with concentrated sulfuric acid with water. Because if we do so, then we will dry it and then pass it again over water, which will cause it not to be dry. So we need to ensure that we start with water, then followed by the concentrated sulfuric acid. So what are some of the physical properties of hydrogen? First of all, uh, they are usually in different states. So fluorine is a pale yellow gas, chlorine is a green yellow gas, bromine is a brown liquid, and iodine is a dark gray solid. You can see their states are changing down the group. They are becoming more and more compacted as you go down the group. That is affected by also their sizes and the strength of their bonds, as you're going to see later on. So you need to remember the colors. Fluorine is pale yellow, chlorine is green yellow, bromine is brown, and it's a liquid, although it can fume to form brown vapors. Iodine is dark gray. It fumes to form purple vapors as well. It can sublime. So when you look at solubility in water, the procedure is a gas containing the halogens, can be chlorine or fluorine, was lowered in a beaker containing water, as you can see from the experiment. And then the experiment was repeated with the other gases in the halogens. So you notice that the level of water rises in the tube after some time, and it rises depending on the solubility of that specific gas. Why does it rise? This is because the gas is occupying a certain space in the boiling tube. The moment this gas lowers and dissolves in water, there is a vacuum that is left inside here. So the water rises to occupy that space that was left. So some of the observations you notice is in the reaction with fluorine, the yellow color of the fluorine will change and the level of the solution will rise. And then in the case of chlorine, also the green yellow color disappears and also the level of water rises in the boiling tube. In the case of bromine, the brown color also disappears and the water also rises in the boiling tube. And in the case of iodine, the solution usually remains the same in the boiling tube. So it tells us that iodine does not dissolve in the same manner like with other gases in this group. So the rise of water is usually higher in fluorine than it is in chlorine. This tells you that fluorine is more reactive with water than chlorine. So the reactivity is coming in very clearly in the fact that which dissolves in water faster. So the moment it dissolves in water, as we said earlier, it creates a partial vacuum. This vacuum is because of where the gas was initially, that space it had occupied. So the water rises in the beaker to occupy that initial space. So they usually dissolve in water to form acidic solution. If you were to use a blue litmus paper, it would turn red, and then a red litmus paper would remain red. Other commercial indicators also can be used. And then the more the soluble the halogen is, as we have said, the higher the rise. So when you look at the solubility, we said fluorine is the most soluble. Iodine does not dissolve very much. So the solubility decreases down the group. The reason why it decreases down the group is because halogens are molecular structures. So when you look at halogens, they are diatomic in nature. They exist in gaseous state, they're atomic. For example, if you look at fluorine, the atom exists in two atoms. You're going to see how we see this in structure bonding. If you look at chlorine, it's a bit larger. If you look at a bromine, it's even larger. So they usually form weak van der Waals forces. So if you take two fluorine molecules, you notice there are some forces in between the molecules. These forces between the molecules is what we refer to as the weak van der Waals forces. So these weak van der Waals forces depend on the size of the atom or the molecule. So during the dissolution, the van der Waals forces must be broken and the strength of the van der Waals forces increase with the atomic size. So if you look at the diagrammatic representation I've just drawn, so the smaller the molecule, that the weaker the van der Waals forces, the bigger the molecule, which is as a result of a bigger atom, will cause to have a stronger, you can see these van der Waals forces look large. They're stronger when the molecule is bigger. So that's the reason why when you look at fluorine, it can dissolve in water fast because these forces can be broken very quickly because they are weak. But for iodine, which is very large, it has very strong van der Waals forces, so the forces cannot be broken as quickly as in fluorine. So another solution is tetrachloromethane. So initially we talked about dissolving in water. So in tetrachloromethane, the same reaction was carried out. A beaker was placed on top of water trough containing tetrachloromethane or a beaker containing tetrachloromethane. And then the boiling tube contains the gases, that is fluorine, chlorine, bromine, and iodine. And then the observations that were noted is that all of them dissolved in the tetrachloromethane. So the solubility is higher in tetrachloromethane than in water because since they are molecular, we usually refer to them as nonpolar. You talk about polarity and nonpolar later on in structure and body, but because they are nonpolar, they do not have those charges. They dissolve more in nonpolar compounds. So water is polar, that is the reason why it doesn't dissolve as much, but tetrachloromethane is nonpolar. Okay, so next we look at the effect of heating these halogens. So fluorine and chlorine are usually gases at room temperature, so they usually slightly expand in volume when heated, while bromine usually forms brown fumes, so it changes to gas. And then iodine sublimes, so it changes from solid to gas directly, so you're going to see some purple fumes. So when you look at electrical conductivity, they do not conduct electricity. The reason why they don't conduct electricity because they are molecular. They do not have particles or they do not have mobile ions, nor do they have localized electrons. So localized electrons occur in metals and then mobile ions usually occur in ionic compounds. And that is these halogens are none of those. So next we look at the melting point and boiling point. So the melting point of halogens increases down the group. So this is contrary to what you have been seeing with alkali and alkaline earth metals when we say that the melting point and boiling point decreases down the group. But for the halogens, since they exist in molecule, so they are in molecular in structure. Molecule is they are diatomic. They exist in two atoms. So they usually held together by van der Waals forces, which have to be broken during bond breaking when they are melting and boiling. The strength of the van der Waals forces increases as the size of the atom increases. So the bigger the atom, the bigger the molecule, the stronger the van der Waals forces. It's just like that. So if you look at fluorine, for example, I'll take this as an example as we had done before. And then you compare it with chlorine, which is a bit bigger. And we go to bromine, which is even bigger. So if you look at the van der Waals forces, which we said they are in between the molecules, you'll notice that the strength of the van der Waals forces is dependent on the strength of the molecule, the size of the molecule, which is dependent on the size of the atom. So the smaller the atom, the smaller the molecule, the weaker the van der Waals forces. The bigger the molecule, the bigger the atom, sorry, the bigger the molecule, the stronger the van der Waals forces. So the reason why the melting point is increasing, we will need more energy to break this strong bond, this strong van der Waals bond that is holding the big molecule that comes from the big atom. While in fluorine, for example, we require less energy to break these weak bonds between the small molecules which come from the small atoms. It goes like that. So this is just an overview of what you have discussed. You notice that the melting point, you can see it's just decreasing down the group, and also the colors of the halogens. Fluorine is pale yellow, chlorine is green yellow, bromine is a brown liquid, and then iodine is a dark gray solid. Some books talk about a black solid. Both chlorine and iodine are halogens. What are halogens? These are elements that have 7 electrons in the outermost shell. So any element that has 7 electrons in the outermost shell, it's an halogen. And then in terms of structure and bonding, explain why the boiling point of chlorine is lower than that of iodine. So chlorine is a smaller atom, or it forms a smaller atomic radius atom than iodine. So it forms smaller molecules than iodine. So the weak van der Waals forces between the molecules of chlorine are weaker than those of iodine. So you can go ahead and say more energy or less energy. In this case, it's less energy is required to break these bonds in chlorine than in iodine. So you see it's a small atom, small molecule, weak van der Waals that are weaker, and then less energy is required. So I've just summarized, but you can put it together in a statement. So next, study the information in the table below and answer the questions that follow. The elements do not represent the actual symbols of the elements. So what is the general name given to the group in which the elements belong to? So this is halogens, and you can see why they have all 7 electrons in the outermost shell. State 2 elements which are colored gases. So we know fluorine, which is X, and chlorine are colored gases. This is pale yellow, this one is green yellow. Explain why Z has the highest boiling point. It is the largest, so it forms the largest molecule with the strongest van der Waals forces. So it will require the highest energy to break these van der Waals forces. And then element Y dissolved in water and a piece of blue litmus paper was put in the resulting solution. State the observation, explain the observation. So the blue litmus paper will turn red. Why? Because element Y dissolves in water to form an acidic solution. That brings us to the end. Later, we are going to continue with some of the chemical properties that are remaining. So see you in the next session.